Today, I will be discussing with you another topic in fluid mechanics. In our previous topic, we discussed about pressure, pressure measuring devices, hydrostatic forces on submerged plane surfaces, hydrostatic forces on submerged curved surfaces, and buoyancy. Today, I will be discussing about the conservation of energy. In the analysis of conservation of energy, there are three equations that is commonly used. The first one is the mass equation. The mass equation is an expression of the conservation of mass principle. The second equation is the Bernoulli equation, which is concerned with the conservation of kinetic, potential, and flow energies of a fluid stream and their conversion to each other in the regions of flow where net viscous forces are negligible and where other restrictive conditions apply. The final equation is the energy equation, which is a statement of the conservation of energy principle. In fluid mechanics, it is found convenient to separate mechanical energy from thermal energy and consider the conversion of mechanical energy to thermal energy as a result of frictional effects as mechanical energy loss. Then the energy equations becomes the mechanical energy balance. In this lesson, you should be able to apply the mass equation to balance the incoming and outgoing flow rates in a flow system. Recognize various forms of mechanical energy and work with energy conversion efficiencies. Understand the use and limitations of Bernoulli equation and apply it to solve a variety of fluid flow problems. And work with the energy equation expression in terms of heads and use it to determine turbine power output and pumping power requirements. This will be the outline of my presentation. So let us start first with you are already familiar with numerous conservation laws such as the laws of conservation of mass, conservation of energy, and conservation of momentum. Historically, the conservation laws are first applied to a fixed quantity of matter called a closed system or just a system, and then extended to a region in space we call the control volumes. In the first conservation law, which is the conservation of mass, the mass of the system remains constant during a process. It is expressed in the rate form as the summation of mass in minus mass out is equals to the rate of change of the mass in the control volume. In fluid mechanics, conservation of mass relation written for a differential control volume is called the continuity equation. Say for example, we have here 2 kg of hydrogen gas and then 16 kg of oxygen gas. By conservation of mass, if you're going to combine them, the resulting mass would be 18 kg since there is 2 kg of hydrogen and 16 kg of oxygen. So in this chemical process, the water has 18 kg in terms of mass. So that is the conservation of mass principle. The second conservation law is the conservation of momentum. The linear momentum, if you are familiar in physics, is just the product of mass and the velocity of a body. According to Newton's second law, the acceleration of a body is proportional to the net force acting on it and is inversely proportional to the mass, such that force is equals to mass times acceleration. The rate of change of the momentum of a body is equal to the net force acting on the body. That is why the momentum of a system remains constant when the net force acting on it is 0, and thus the momentum of such system is conserved. In fluid mechanics, Newton's second law is usually referred to as the linear momentum equation. The third conservation law is the conservation of energy. The net energy transferred to or from a system during a process be equal to the change in the energy content of the system. By conservation of energy, it is given in the equation the rate of change of energy, the energy in minus the energy out is equals to the differential change in the energy in the control volume per unit time. Now that we are already familiar with the conservation laws, we will tackle another important concept, which is mechanical energy and efficiency. Many fluid systems are designed to transport a fluid from one location to another at a specified flow rate, velocity, and elevation difference. And the system may generate mechanical work in a turbine, or it may consume mechanical work such as in a pump or fan during this process. These systems do not involve the conversion of nuclear, chemical, or thermal energy to mechanical energy. Also, they do not involve any heat transfer in any significant amount, and they operate essentially at constant temperature. Such a system can be analyzed conveniently by considering the mechanical forms of energy only and the frictional effects that cause the mechanical energy to be lost, such that it will be converted to thermal energy that usually cannot be used for any useful purposes. When we say mechanical energy, it is a form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. Example of forms of mechanical energy are kinetic and potential energies. Other energy that is not considered as mechanical energy are thermal energy, since it cannot be converted to work directly and completely, according to the second law of thermodynamics. In unit mass, the mechanical energy is defined as pressure divided by the density plus velocity squared divided by 2 plus the product of acceleration due to gravity and z. In this equation, the first term is what we call the flow work. So when we say flow work, it is, for example, when a pump transfers mechanical energy to a fluid by raising its pressure. As you can see, in a turbine, it extracts mechanical energy by dropping its pressure. So that kind of work is what we call the pressure work. Therefore, the pressure of a flowing fluid is associated with its mechanical energy, and that's what we call the flow work. The second one is the kinetic energy, which is we are already familiar in physics. And the third component of mechanical energy is the potential energy. So when we say mechanical energy, it is just a sum of flow work, kinetic energy, and potential energy. Therefore, the mechanical energy of a fluid does not change during the flow if its pressure, density, velocity, and elevation remains constant. You can see here in this equation that for incompressible flow, so if you can still recall when I say incompressible flow, it is a kind of flow that does not involve change in volume or density. The change in mechanical energy is just the change of those value of flow, kinetic, and potential energy. Say for example, in a hydroelectric power plant as an example. So the reason why we can generate electricity is because of the change in pressure of the water, change on velocity of the water as it enters the turbine and leaves it, and also the elevation. That is the reason why we have to stock the water at a higher elevation before we release them for the power production. So that is what we call the change in mechanical energy for an incompressible flow. So just like before, the first term is what we call the change and flow work. The second term is the change in kinetic energy. And the third term is the change in potential energy. Mechanical energy is defined as in this formula that you can see in the equation. The transfer of mechanical energy is usually accomplished by rotating a shaft, for example, and thus mechanical work is often referred to as shaft work. A pump or a fan receives shaft work, usually from an electric motor, and transfer it to the fluid as a mechanical energy, less the frictional losses, of course. A turbine, on the other hand, converts the mechanical energy of a fluid to shaft work. In the absence of any irreversibility such as friction, mechanical energy can be converted entirely from one mechanical form to another. And the mechanical efficiency of a device or a process can be defined in this equation that you can see here. It is defined as the mechanical energy output divided by the mechanical energy input. So what you put into the system and what you receive from the system as a result of that. In terms of the loss, it is just defined as 1 minus the mechanical energy loss divided by the mechanical energy input. So that is our mechanical efficiency. As you can see, it is just our desired quantity, which is the output, which is the electricity, for example, divided by the input, maybe the mechanical energy from a fluid to turn a turbine. So that's the mechanical efficiency. So as you can see here, the mechanical efficiency of a fan, for example, is the ratio of the kinetic energy of air at the fan exit, which is the output, to the mechanical power, which is the input. So the input comes from, for example, the electricity in order to rotate the fan. The mechanical energy of two common devices that is used in fluid mechanics, such as the pump and the turbine, is defined as follows. For the pump efficiency, it is just defined as the mechanical energy increase of the fluid divided by the mechanical energy input. So in equation form, it is denoted by the symbol. It is the change in mechanical energy of the fluid divided by the shaft. So since the input is from the rotating shaft, if you can see an actual operation of a pump, it is connected to a motor which produces shaft rotation. So that is the work of the shaft in order to rotate the pump. There is the output is the increase in the energy of the fluid, because the purpose of the pump is to increase the mechanical energy of the fluid by putting in by the rotation of the shaft. So it can also be written in this form: the useful pump work, which is the output, divided by the work needed for the pump, which is the electrical input in the pump. So the change in mechanical energy of the fluid is defined for the pump as the mechanical energy output minus the mechanical energy input. So it is expected that the output for a pump is greater than the input because you added energy to the fluid. So that's the purpose of a pump. That's why we can raise or transfer water from one elevation to a higher elevation because of that. For the turbine efficiency, it's just the inverse. It is mechanical energy output divided by the decrease in mechanical energy of the fluid. So the output is the shaft output, which is if you connect it, say for example, to a generator. So that's the output divided by the change in mechanical energy of the fluids. This is an absolute value because this is actually will have a negative because it's a decrease. But for the efficiency, we don't have negative. That's why we make it absolute value. And we can also write this in terms of work turbine divided by the turbine work extracted. So our mechanical change in mechanical energy of the fluid is mechanical energy in minus mechanical energy out, because as you can, if you can still you can see an actual operation of a turbine, the mechanical energy input, say for example from the water, is greater than the output, which is the one that you can produce from the turbine. So that's the turbine efficiency. So in fluid systems, we are usually interested in increasing the pressure, velocity, and elevation of a fluid. So this is done by supplying mechanical energy to the fluid by using a fan, a, a pump, or a compressor. All of these are actually referred to as pumps. Or we are interested in the reverse process of extracting mechanical energy from a fluid by a turbine and producing mechanical power in the form of rotating shaft that can drive a generator or any other rotary device. The degree of perfection of the conversion process between the mechanical work supplied or extracted and the mechanical energy of the fluid is expressed by the pump efficiency and the turbine efficiency. So that's why they are important quantities. The mechanical energy should not be confused with the motor efficiency and the generator efficiency. So when we say motor efficiency, it is the mechanical power output divided by the electrical power input in order to drive the motor. So it is the shaft work output of the motor divided by the electrical input needed to drive the motor. For the generator efficiency, it is the electric power output divided by the mechanical power input. So say for example, when you connect a turbine to a generator, the turbine will produce this mechanical power input. The product of the generator will then be the electrical power output. And they can be written in this way: electrical output divided by shaft input. Say for example, we have here a turbine generator. The overall efficiency of a turbine generator is the product of the efficiency of the turbine and the efficiency of the generator. And it represents the fraction of the mechanical energy of the fluid from what is extracted by the turbine to the energy converted to electrical energy by the generator. As you can see here, the efficiency of the turbine is 0.75. The efficiency of the generator is 0.97. So the turbine generator overall efficiency is just the product of these two efficiencies. So let us have an example. So we have our example number 1. The water in the lake is to be used to generate electricity by the installation of a hydraulic turbine generator at a location where the depth of the water is 50 meters. Water is to be supplied at a rate of 5,000 kilograms per second. If the electric power generated is measured to be 1,862 kilowatt and the generator efficiency is 95%, determine the overall efficiency of the turbine generator, the mechanical efficiency of the turbine, and the shaft power supplied by the turbine to the generator. So here is the illustration. We have here a lake. So the depth of the lake is 50 meters. So at the bottom of the lake, we extract water at a rate of 5,000 kilograms. So you can imagine how enormous that is. So per second, it's 5,000 kilograms. The rotation of the shaft of the turbine will drive the generator. That's the reason why we can produce electricity. So the generator produces 1,862 kilowatt. So this electricity will then be distributed. But still, there are still losses during the distribution. That's why we have distribution loss. But the efficiency of this generator is 0.95 or 95%. So take note that it is expected that there is also an efficiency of the turbine. And we can compute that by computing first the potential power that we can harvest from this lake. So that is the input. And then the output is what the turbine will actually be able to produce given the condition that we have here. So in this problem, we are given with the depth of 50 meter, the mass flow rate of 5,000 kilogram per second, the electrical power output of 1,862 kilowatt, the generator efficiency of 95%. The unknown are the turbine generator efficiency, the turbine efficiency, and the shaft power supplied by the turbine to the generator. So that is the power between turbine and generator. That's the work shaft output. So the change in the mechanical energy of the fluid in a turbine based on the previous slide is defined as the change in mechanical energy of the fluid, which is the mechanical energy input minus mechanical energy output. So take note that for a turbine, the input, which is from the water, the input from the water, the power that we can harvest from the water, that's the usually it's called water horsepower, minus the mechanical energy output, which is the one that will be produced, no, which is can be measured by the rotation of the shaft. So that's the mechanical output. So the input is in the input side of the turbine, the output is here in the shaft. So that's the change in the mechanical energy of the fluid. So in mass flow rate form, we can actually write that in this way. So when the small letter means it's in a unit of kilojoules per kilogram. So when we multiply it with kilogram per second, we can get kilojoules per second or kilowatt. And in our lesson, it is defined as the mass flow rate multiplied by the change of mechanical energy of the fluid, which is just the difference between the pressure, the velocity, the pressure energy, which is the flow energy, the kinetic energy, and the flow energy, the potential energy rather, at the inlet and the outlet of the turbine. So that's why we have this equation here multiplied by the mass flow rate. The kinetic and potential energies of the water are negligible, so we can just neglect them. Say for example that the velocity of the water here at the surface of the lake is 0, so meaning it's just negligible, and then at the outlet it's just also negligible because we can consider it as still water already. The potential energies can also be considered as 0 for the water. So that's why we can write the change in mechanical energy of the fluid in this form. So if we cancel out the kinetic and potential energy, then the change in mechanical energy is just the product of the mass flow rate and the change and the flow energy, which is P1 minus P2 divided by the density, which is also equivalent to the mass flow rate, the gravity, and the height. Because if you can still remember, our P1 minus P2 divided by rho is just equals to the gravity and the height. So by substitution, we can write the change in mechanical energy of the fluid as this one. So we have the mechanical energy is 2,452,500 watt, or 2,452.5 kilowatt. So the overall efficiency can now be computed using the formula, the electrical power output divided by the change of mechanical energy of the fluid. So by substitution, the turbine generator efficiency is 75.92%. So therefore, the amount of energy that can actually be generated from the water by extracting energy from the lake is 75.92%. It means that around the remaining 24% are converted to other forms of energy that is not useful at all. So they are losses already. So that's what we mean by the turbine generator efficiency. So our purpose as engineer is to really improve the efficiency by improving the design of the turbine, the generator, and all those components that causes the losses in the efficiency. So now that we have the turbine generator efficiency, then we can now compute the turbine efficiency by using the relationship between them, which is the product of the turbine and generator efficiency. So by substituting the value that we already know, we can get the turbine efficiency as 79.92%. So the efficiency of the turbine alone is 79.92%. So also from the relationship, which is defined as the efficiency of the turbine, is just the shaft output. So which is the output here at the shaft at the outlet of the turbine divided by the change in mechanical energy of the fluid, which is the water horsepower. So if we substitute the values, we can get the shaft output also. So the shaft power supplied by the turbine to the generator is 1960.038 kilowatt. So if we're going to summarize our answer, so we have potential energy coming from the lake that causes the rotation of the turbine, and it is coupled to the generator which produces this 1862 kilowatt. It is obvious that the power extracted here should be greater than this one because there are losses along the way. So we computed that as the change in mechanical energy of the fluid, which is 2452.5 kilowatt. And because the turbine is not perfect, it has an efficiency of 79.92%. 20% of this 2452.5 kilowatt is lost in the friction, maybe because of the friction in the shaftings of the turbine. So as a result, the shaft output is less already by 20% from this value. So that's 1960.038 kilowatt. So that is the power delivered by the shaft of the turbine to the generator. And since the generator is not perfect, it will also reduce around 5% from this 1960 in order to finally produce the 1862 kilowatt. So that is the relationship between those quantities that we calculated in that particular example. Note that the lake supplies 2452.5 kilowatt of mechanical energy to the turbine, which it converts 1960.038 kilowatt to shaft work that drives the generator, which generates 1862 kilowatt of electric power. So there are irreversible losses through each of the components, such as the turbine, the shafting, and the generator. So now that we are already familiar with the different form of mechanical energy and efficiency, we are now ready to dive into the different conservation law. The first one is the continuity equation. For closed system, the conservation of mass principle is implicitly used by requiring that the mass of the system remains constant during a process. So that's why it's conservation of mass. For controlled volumes, on the other hand, a mass can cross the boundaries. So say for example, for a turbine, a mass of water can cross the boundary of the turbine. It will not stuck in the turbine. So when it is stuck in the turbine, or for example, it will stuck in a system, say for example, a piston cylinder arrangement wherein a fixed amount of gas is stuck there. That is a closed system. But here, since the mass can cross the boundary, it's considered as control volume. And so we must keep track of the amount of mass that enters that control volume and leaves that control volume. So it can be defined using this mass flow rate and volume flow rates. The mass flow rate is defined as the amount of mass flowing through a cross section per unit time. So for compressible or incompressible flow, it means constant density. this can be applied. So this formula can still be applied. So the mass flow rate is just a product of the density of the fluid multiplied by the average velocity of the fluid and the cross-sectional area of the flow. So the unit here would be in kilogram per second. The volume flow rate, on the other hand, is defined as the volume of a fluid flowing through a cross-section per unit time. So it is defined as the average velocity multiplied by the cross-sectional area. So it is meter cube per second. So the relationship between the mass flow rate and volume flow rate is the mass flow rate is the product of density and the volume flow rate. So meaning if you have these quantities, then you can obtain the mass flow rate and volume flow rate. So whenever you have the volume flow rate and you have the density, then you can get the mass flow rate. Whenever you have the mass flow rate and you don't have the volume flow rate, then you can just divide it by the density so that you can get the volume flow rates. The conservation of mass principle. The equations are often referred to as the mass balance and are applicable to any controlled volume undergoing any kind of process. So this is the conservation of mass principle. It is stated as the net mass transfer to or from a controlled volume during a time interval is equal to the net change, whether increase or decrease in the total mass within the controlled volume during the time interval. So in equation form, the mass in minus mass out is equal to the change in the mass in that control volume. So the unit is in kilogram because it doesn't have a dot. In terms of rate, so meaning it's in per second, so it has a dot. So that's why we have it. M dot in minus M dot out is just the rate of change of the mass in that control volume. Or say for example you have many masses entering and many masses going out, because there are also devices that has multiple entry points and multiple exit points. Then the conservation of mass principle can be written in this way: the summation of mass entering minus the summation of mass exiting is equal to the rate of change of the mass of the control volume per unit time. Say for example you have a bathtub. So an amount of water entering into the bathtub, which is 50 kilogram, and then a mass of 30 kilogram is going out as a result of this port here. So the change of mass in the bathtub is just the mass in minus the mass out. So that is 50 kilogram minus 30 kilogram. So that's 20 kilogram. So that's basically a conservation of mass principle that is applied there in that system. The mass balance for steady flow processes. Steady flow processes are those processes wherein the total amount of mass contained within a control volume does not change with time. So that's why it's steady flow. So meaning there is no change in the total amount of mass contained. That's our MCV is constant. So for example that 20 kilogram in the bathtub is constant, so it is not changing. So that's why it's steady flow process. For steady flow processes, the total flow rate of the mass entering a controlled volume is equal to the total rate of mass leaving it. So in equation form, if we have a steady flow process, the summation of mass in is just equal to the summation of mass out of that controlled volume. For steady flow, wherein we have single stream, an example of this device are the nozzles, diffusers, turbines, compressors, and pumps. They have single streams, meaning there is only one input, there is only one exit point. So the steady flow process equation for the conservation of mass can be written as mass entering is just equal to mass exiting. We can also write it in this way, since we already defined mass flow rate as the product of density, the velocity, and the area. It should always be kept in mind that there is no such thing as a conservation of volume principle. Therefore, the volume flow rates into and out of a steady flow device may be different. As you can see here, the volume flow rate is different, that is 1.4 at the entrance of this air compressor and 0.8 meter cube per second at the exit. However, since the mass is conserved, the mass at the inlet and the outlet would be the same. That's why conservation of mass is a check, while conservation of volume does not exist. So this is due to the higher density of air, for example, at the compressor exit. For steady flow fluids, however, the volume flow rates as well as the mass flow rates remain constant since the liquid are essentially incompressible. Water flow through a nozzle of a garden hose is an example of a latter case. The conservation of mass principle is based on experimental observation and requires every bit of mass to be accounted by during a process. If you can balance your checkbook by keeping track of deposits and withdrawals, or by simply observing the conservation of money principle, you should have no difficulty applying the conservation of mass principle to the engineering system. So we have here another example. A garden hose attached with a nozzle is used to fill a 10-gallon bucket. The inner diameter of the hose is 2 cm and it reduces to 0.8 cm at the nozzle exit. If it takes 50 seconds to fill the bucket with water, determine the volume and mass flow rates of water through the hose and the average velocity of the water at the nozzle exit. So this is the illustration. So we have a hose which has a diameter of 2 cm, and then we have a nozzle here which reduces it to 0.8 cm diameter at the exit. So it is used to fill this bucket, which is 10 kilogram in volume. So it takes 50 seconds to fill this bucket, and we are looking for the volume flow rate, the mass flow rate, and the average velocity of water at the nozzle exit. So the given are the volume, which is 10 gallon, the diameter at the exit of the nozzle, which is 0.8 cm, the time interval, which is delta t, which is 50 seconds. The unknown are the mass flow rate, the volume flow rate, and the average velocity of the water at the nozzle exit, or VE. So for steady flow and compressible flow, so this is steady because again there is no change in volume. As you can see here, for example, at the bucket, if this is the system, the volume here would not change. So that is a steady flow, and then it will remain 10 gallon. In compressible flow, in the other hand, because we cannot change the density of the water by just doing this process, so there's no change in the water is incompressible on the other hand. So if we use this relationship for steady flow and compressible flow, our volume flow rate is just equals to the velocity divided by the time interval. So we just convert the 10 gallon first to liter and divide it by delta t so that we can get the volume flow rate, and that is 0.7571 liter per second. For the mass flow rate, it's just the product of density and the volume flow rate. So our density of the water is 1 kilogram per liter. So if that is in kilogram per meter cube, that's 1,000. Per liter, that is 1. So our mass flow rate is 0.7571 kilogram per second. So we already have the volume flow rate and the mass flow rate. The average velocity of the exit, so we look at the nozzle exit here. So as you can see, we need here to get the average velocity. If we are familiar, we actually have this relationship, which is the volume flow rate is the area at the exit, the area times the velocity, right? So that's why we have volume flow rate is the area at the exit multiplied by the velocity of water at the nozzle exit, or VE. So here we can get the value of VE by substituting the value of the area, which is pi over 4 d squared. So that's just the area of the exit which is a circular. That's why it's pi over 4d squared. So substituting the known value, we can get the VE as the unknown. So the velocity, the average velocity of water at the nozzle exit would be 15.1 meter per second. So it can be shown that the average velocity in the hose, if you're going to compute it, is actually 2.4 meter per second. So at the hose, the velocity is 2.4 meter per second. In the nozzle, it is 15.1 meter per second. So as a result, by installing a nozzle at the hose, you increases the water velocity by over 6 times. So that's the reason why it's actually useful to attach a nozzle at the hose if your purpose is to increase the water velocity. So we have here another example. So we have a 4 feet high, 3 feet diameter cylindrical water tank. So if you can see the cylindrical the water tank that is used commonly, it's cylindrical. So that is an example. This is an example of that. So the tap is open to the atmosphere and is initially filled with water. As you can see here, it's full of water. So this will be our control volume. This portion here, this system of water. Now the discharge plug near the bottom of the tank is pulled out, and the water jet, whose diameter is 0.5 inch, streams out, as you can see here. The average velocity of the jet is given by the equation square root of 2gh, where h is the height of the water in the tank measured from the center of the hole. So the center of this jet diameter here to a variable height h, and g, which is the gravitational acceleration. So we are to determine how long it will take for the water level in the tank to drop to 2 feet from the bottom. So we are going to compute for the time that needed in order to drain half the amount of the water, which is, since it is 4 feet high, meaning it's half because it's 2 feet from the bottom. So we are given with the full height, which is the height when it is full. The height of water when it is full, it's 4 feet. The diameter of the tank, which is 3 feet. The diameter of the jet, which is 0.5 inch. The unknown are the delta T, or which is the time, how long it will take for the water level in the tank to drop 2 feet from the bottom. So from the conservation of mass relation for a controlled volume undergoing any process, we can use this relationship because here in this problem, we are dealing with change in the mass in this controlled volume per unit time. During this process, no mass enters the controlled volume. So there is no water entering, only water exiting. So that's why we can reduce this relationship by canceling out mass in into negative mass out is equals to the rate of change of the mass here in the controlled volume. The mass flow rate of the discharged water can be computed using the formula, the product of density, the velocity, and the area at the outlet. So if you're going to substitute the value, since V is given as square root of 2gh, take note that the outlet is also the jet, because this is the outlet here at this portion. So that's why the area here is the area of the jet. So we also express the area in terms of the diameter of the jet, as you can see here. So this is now the mass flow rate of the discharge water here. So the mass of the water in the tank at any time, if we analyze the control volume, the mass of the water in the tank at any time is just a product of the density and the volume. So we know that we are not looking here for the rate, but just the mass of the water at any time at any volume V. So since density is mass over volume, so that's why we have mass is density times volume. So this is volume, so do not be confused with volume and V, which is velocity. So it's very confusing for fluid mechanics really. So the volume of the tank is can also be written because it's cylinder. So the volume of the cylinder, which is the area of the base, which is the area of the tank, multiplied by the variable height. Because the mass actually here is varying because it is changing depending on the amount of water, right? So substituting the area of the tank, which is just the pi over 4 diameter of the tank squared. So we have here this mass flow rate of the water in the tank at any time. At any time, because H again is a variable, it's changing. The height of the water in the tank is changing. So now that we have the MCV and the mass flow rate out, we will substitute it here in this equation that we have a while ago. So by substitution, we have these values, as you can see, in terms of dt. So our goal is to solve for the value of time. So to solve the value of time, then we will have to differentiate that particular equation. But before we do that, we will first not differentiate, but we're going to integrate because we are given with differential values. So to get the whole from the small values, small quantities, we will have to integrate or to sum it up. So if we are going to rearrange the previous equation such that the dt will be the variable on the left side of the equation, and then the right equation will be in terms of the height h, then we would obtain this equation here. Since the diameter of the tank and the diameter of the jet is constant, we can separate that from the variable, which is dh divided by the square root of 2gh. So by integrating from 0 to time t, the value of dt, so we'll also integrate the value on the right side from the height 0, which is the full height of the tank, of the water level in the tank, to a height 2, which is 2 feet from the bottom. That is our h2. As you can see here, that's the h2. So we integrate. We can use calculator anyway, since we can still use calculator in the board exam, then we can use that now. So just type this in the calculator. You can obtain the value of delta t as 756.82179 seconds, or in minute, that is 12.6136 minute. So if we use the same relation, this same relationship here that we already obtained in terms of dt and dh, the discharge time for the entire amount of water in the tank would be 43.1 minutes. So if only half of the tank will be discharged, it will take 12.61 minutes. But if you discharge the whole volume of water, it will take 43.1 minutes. What can we obtain from this? Therefore, emptying the bottom half of the tank takes much longer than emptying the top half of the tank. This is because the decrease in the average discharge velocity of the water is decreasing because of the height.